Hello everyone, in this video I want to look at how to plot the titration curve for a weak base, ethylamine, titrated with a strong acid, HCl. Alright, so thinking of what our titration looks like, we're told that we're titrating ethylamine, so that's C2H5NH2, alright, with HCl. So in our burette, we place HCl. And that is our titration setup. So in other words, we start with the base, that is our titrant, and we are going to add HCl to it. And we need to discuss what is our net ionic equation, what is our expectations for the pH curve, and so on. So right, the base, of course, being a weak base, its active form in solution will of course just be the base itself. So it's the C2H5NH2. The strong acid will react in the form of hydronium, so that would be H3O plus aqueous, and these will react to form the protonated form of the base, so C2H5, and the base contains nitrogen, so that means that would be the species that is protonated, NH3 plus then aqueous. Right? If you struggle to see where it's protonated, you can draw the Lewis structure, look up the structure to check that. And if hydronium is deprotonated, that means there's water also then formed during this. But we notice that during this process, right, we have the base being protonated, forming its conjugate acid. So therefore it means this conjugate acid should, once it's starting to form, it should be able to hydrolyze with the waters. In other words, it can hydrolyze and react again with the water to form hydronium and the base again. So therefore it means we should actually think of this titration as an equilibrium in H2 aqueous. Meaning, I'll use the word should, it means it might assist us to think of this titration as an equilibrium, just because it means there is this forward reaction forming C2H5 NH3 plus aqueous, right? But it means that there is a reverse reaction, right? So when C2H5NH3 plus reacts with water, hydrolyzes with water, it would again then form the conjugate base and hydronium. All right, and that means there is a possibility of this equilibrium. All right, and that's while we are adding the H3O plus. It also means that once we reach equivalence point in this titration, right? So once we've added enough of the reactants, so meaning enough, once the amount of acid equals the amount of base we have initially, that means we will only be left with the conjugate acid and water. And hence we should then think of this equilibrium as flipping around or switching around, because then in principle the equilibrium will be dictated, or the pH will be dictated by this conjugate acid species. So the C2H5NH3 plus aqueous species hydrolyzing with the water to form a weak equilibrium and forming H5 NH2 aqueous plus H3O plus, causing our equivalence point to have a pH slightly less than 7, right, because of the presence of this hydronium at this equilibrium. All right, so this is our initial analysis, or what our initial analysis tells us, is that even though we're adding hydronium just to the base, this base forms its conjugate acid, and therefore we must think of it as an equilibrium. And therefore, at the equivalence point, when we've added equal amounts of acid to the base, this equilibrium will flip around, because the main amount, the excess amount in this equilibrium will then be this, and then the dictating, or the what do you call it, the favored reaction will then be this reaction. It will be the reverse reaction. So we can think of the equilibrium as being, this is the forward equilibrium, or the forward reaction then, and this is the reverse reaction then. All right, so that is what it is, and therefore making the formation of this hydronium pushes the pH lower. All right, so let's just review that again in terms of what we expect for our pH curve, or our titration curve. If you have pH plotted against volume of HCl added, we know we start with a base, right? C2H5NH2 is a base. And the reason I say that is, I mean, it's not given in the question. If you look it up, then you will notice that it has a Kb value. So you start here with a pH higher than 7, a high pH. And then we should expect to, this is a terrible curve, to see something like that, right? We will have a period where our pH decreases, we will reach equivalence point, and our equivalence point will be acidic. We will have an equivalence point with a pH less than 7. Why? Because of this hydrolysis of the conjugate acid, forming hydronium. All right. Other important things that we must remember, that while we are initially adding the strong acid, the HCl, right, it forms it reacts with the base, leaving the base in excess, but forming the conjugate acid. So therefore, initially we have a region where we have the base and its conjugate acid in relative amounts. So therefore we have a buffer region. Before we reach the equivalence point. And after we've reached the equivalence point, we will have an excess amount of HCl. In other words, an excess amount of hydronium added. And the excess amount of hydronium added will dictate the pH at this point. All right, so that is our important points in this titration that will dictate the different areas in this. So that is what is the important areas that we need to consider. All right, so let's look at the volumes that we should consider here. So in the first part, we're asked, of course, what is the pH at the beginning before any HCl is added? So before any HCl is added, we're actually just looking at what is the pH of our initial solution in the conical flask. So we're interested in what is we have a base dissolved in water, and this base is allowed to hydrolyze to form its conjugate base, conjugate acid and hydroxide. And this hydroxide will dictate the pH. So what we need to do is, this is a question of what is the pH of a given base concentration. So we need to look up its Kb value and then determine the concentration of the OH, and from that we can determine the pH. Alright, and I've done that for us. So you will see it's a bit of work, but you have the initial concentration. The initial concentration of these species are 0. You use your mass balance table to set up the Kb expression. You look up the value for Kb, which is 4.27 times 10 to the negative 4, and you will get a quadratic expression. One of the values aren't valid because it's negative. And then you can use the OH concentration at equilibrium to solve for the POH, and that will give you the pH from the POH. All right, so that's our first concentration, our first pH. And we see that it's indeed basic, right? Because we have a base, and that's as expected. Good. The next question is, what is the pH at the halfway point in the titration? So the halfway point is, of course, here in the buffer region. And by definition, the halfway point is where we have the amount of conjugate acid formed, or the amount of conjugate formed, equal to the amount of whatever the other species is. So our conjugate acid base pair or base conjugate acid pair are equal in the buffer region. So we're halfway to the equivalence point. And what that actually means is that the pH is equal to the pKa. But we have a base in this case, right? So it does not have a pKa, or it has a pKa, but we have the Kb for this species. So if the pH is equal to the pKa, it means we can use the pKb because we have the Kb for this species. And that would mean pH is equal to pKa, which is 14 minus pKb, because the pKa and the pKb work the same as the pH and the pOH. And then we can calculate the pH from that. All right, so this is the basic use of, you must just remember what the definition of the halfway point is. So the halfway point is that region in the buffer region where the pH is equal to the pKa. But hopefully you remember this is a base that we're looking at. So we have the Kb of the base, so you can use its pKb. If you wanted to use a pKa, what Ka value would you use? Well, it would of course be the Ka value of the conjugate acid, right? So that's what it actually is. You must use the Ka of the conjugate acid, right? Or the acid. So it's always the acid base pair that you're looking at, and it's the pKa of the one that is the acid. Okay, so it's just because we have the Kb of the base, we must use the pKb in this case to calculate the pKa. All right, so that's what's going on there. Cool. Question C. When 75% of the required acid is added, what is the pH in this case? So now, what is the pH when 75% of the acid is added? So our first question actually is the stoichiometry problem. So we must first know what is the total amount of base. So the number of mole of base is of course equal to the volume times the concentration. So we see we have 7.5 mole of base because we have 50 milliliter times 0.15 molar. So that means we have 7.5 mole of the base. And so if 75% of the acid have been added, so it means that is 75% of 7.5 mole, that gives us 5.625 mole of acid has been added. Okay, so that's what we have added. So that means that so much acid has been added, HCl is added. We had so much mole of the base originally, but the question is, what is the volume of acid then added? And we can calculate that from the concentration of acid. So it's the number of mole of acid divided by the concentration. That gives us 56.25 milliliter of acid added. Okay, so now we know a couple of things. We also know that our acid is our limiting reactant, right? Because we're not yet at equivalence point. We've only reached 75% equivalence point. So we need to know what is the amount of base in excess. We need to know how much of the conjugate acid has formed, right? And that will of course be dictated by the limiting reactant, which is the HCl. And then we need the concentrations, because that's why we were interested in what the volume is of our HCl. Because in what region are we? We are at the moment in the buffer region. And if we're in the buffer region, the pH will be dictated by the Henderson-Hasselbalch equation, and hence we need the concentrations of our conjugate base, of our base and our conjugate acid. All right, and that's what we're after. So we calculate that. the amount of base in excess is the initial amount minus the amount reacted, so it's the acid amount. So that gives us so much in excess, and its concentration is divided by the total volume. There was 50 milliliter of base to start with, and we've calculated the amount of acid volume added, so that's 56.25 milliliter, gives us 106.25 milliliters total volume, gives us a concentration. The amount of conjugate acid formed is dictated by the limiting reactant, so that's the number of moles now here, and then we can calculate its concentration. So it's this number of moles divided by the total volume, giving us a concentration. Because we are in the buffer region, we then use the Henderson-Hasselbalch equation, right? Plug in our values to calculate the Ka, right? This is the Ka of the acid. We have the Kb of the base. So then we need to use our relationship between Ka, Kb, and Kw. Importantly, so remember, you can't just use the Kb of the base, you need to use the Ka of the acid. And remember where the acid and the base go. So this is the concentration of the conjugate of the base and the concentration of the acid. All right, and I get 10.5153 for the pH over here. 3 significant figures because we have 4.27 as our value for Kb. All right, the next important point that we want to look at is equivalence point. So that's when the number of mole of acid now added equals the number of mole of the ethyl amine. And again, so it's a stoichiometry problem. So at equivalence point, number of mole of acid added equals our base. And the number of mole of base that we started with didn't change. So, I mean, it's because it's the number of mole that we started with. So it's 7.5. So that means we've added now 7.5 mole of acid. And if we added 7.5 mole of acid, it means the volume of acid added is then 75 mole. And that you calculate from the concentration. So it's the number of mole divided by the concentration. So that tells you how many milliliter of acid you've added. Okay, so that means the total volume of solution now must be 125 milliliter. All right, good, that is what we have. Being at equivalence point, it means our reactants have been fully consumed. So we've added the same amount, right? So this is fully consumed. We have 0 mole of this left, and this has been fully consumed, and they've all been converted to the product, to the conjugate base, to the conjugate acid. So it's the only thing that can dictate the pH. All right, and therefore we're interested in what its concentration is. Its concentration, or its number of moles first, is dictated by the amount of HCl added, or the amount of base that you had initially. Neither of them are limiting or excess, so it's just the number of mole. And therefore, it's the number of mole divided by the total volume, which is 125 mole at the moment, gives us the concentration. All right, and now the question is, what is the dictating, what is the equilibrium that we are interested in? Well, it's the reverse equilibria here. So what we do is we flip it around. So this is a weak acid, and it will have an effect on the pH. It can hydrolyze with water, like we've discussed before, forming the base and hydronium again, and it has a concentration of 0.06. So it's summarized in your mass balance table. We need, however, its Ka value, so we can calculate that from the Kb of the base, because they're acid-base conjugate pairs, and then you can calculate the pH using the hydronium ion concentration as here. Okay, so there we go. That is what you do there. It's a normal equilibrium problem here at equivalence point. You just need to realize what species concentration you need, and then you can calculate the pH. So basically the question here is, what is the concentration of the acid? What is the acid? And then you want to know what is the pH of this acid solution. All right, and then as normal, that pH concentration is dictated, or that pH is dictated by the hydronium ion concentration at equilibrium. All right, good. So that is at equivalence point. We're now interested finally in when 10 milliliter more of HCl is added, what is the pH? So in other words, we're now here. What is the pH when an excess amount of hydronium is added? And when an excess amount of added, in other words, past the equivalence point, the pH will be dictated by this excess concentration. So the 10 milliliter excess, let's just calculate how many moles of HCl is in excess, because that then will give us the way to calculate the concentration of hydronium in excess. All right, so we calculate 10 milliliter in excess, means that we have 1.0 times 10 to the negative 3 mole of HCl in excess. Okay, we know that the equivalence point required 10 milliliter of HCl, so 10 milliliter excess means that we've added 85 milliliter of HCl in total, and therefore our total volume is 135 milliliter. And if that is the case, that means the concentration of HCl, which is a strong acid, it fully ionizes, so we can equate its concentration to the hydronium, is then equal to this number of mole in excess divided by the total volume, giving us a concentration for the hydronium of 7.4. And if we have the concentration of hydronium, calculating the pH is a simple matter of taking the negative log of that concentration. And we see we have a very acidic pH. All right, so once you reach the excess point, that's the calculations become quite simple. All right, so that is point number E. All that's left now is to look at actually plotting the titration curve and looking at some indicators. And I've gone ahead and done that nicely in Excel. So there are tabulated values of all the volumes, and I've extrapolated a bit of it, and you'll notice an interesting feature of it, and I'll make a little mention of it. So there you see, there's our pH that we start with, there's our halfway point, there's our 75%, there's our equivalence point, and there is our 10 milliliter extra at 85 milliliter. All right, and you see it follows the predicted pattern that we had. All right. Some things that we can highlight in the buffer region, as we said, we can use the Henderson-Hasselbalch equation, and just importantly remember that it's the concentration of the base and the acid, but of the acid-base conjugate pair, right? It's not the acid and the base that you are titrating with, it's the acid-base conjugate pair concentrations that you use in the Henderson-Hasselbalch equation. At the halfway point, so meaning halfway to the equivalence point, so you can see it's very nicely put halfway in the titration curve, the pH is always equal to the pKa, and that is the pKa of the acid here in the Henderson-Hasselbalch equation. Why? Because at this halfway point, these two values will be equal to each other, right? So you get pH is equal to pKa plus log of 1. And we've done that in an earlier video, so that's why I didn't specify it in this. So you must look at the Ka of the acid. So if in this case it was the conjugate acid that we looked at, the pKa of the conjugate acid. But if you have a weak acid with and titrating it with a strong base, it will be the pKa of the weak acid. Right, but okay. So that's why it's always pH is equal to pKa that you have here. That's for the halfway point. So that's what we do in the buffer region. Our initial pH is of course always dictated by what you have in the flask. So whatever you have in the flask, that is just going to dictate your pH. If you have a weak acid or a strong, or a weak acid or a weak base, you of course just look at its equilibrium that it forms with water, and you use its Ka or Kb value to determine what its pH will be. At equivalence point, we need to remember that that gives us where the number of mole of whatever you're adding is going to be equal to the number of mole of whatever you are titrating. And because we are titrating a weak base with a strong acid, it formed a conjugate acid in this case, right? So this conjugate acid could hydrolyze, and that is why we got an equivalence point that had a pH which was less than 7. Okay, and we can see that because we got 5.9 which was less than 7. So there you can see it's set there, almost looks like it was at 6, but 5.93. Okay, and then once we move past the equivalence point, in this case we're titrating with HCl, so that means the pH, once it moves past the equivalence point, starts getting dictated by the excess amount of acid added, just because the HCl is a strong acid, so that acid ionizes fully, so it is able to dominate and dictate the pH, and its concentration then will then dictate what the pH is, right? So then pH is equal to negative the log of the hydronium ion concentration. So whatever the number of moles are that you have added here, divided by the total volume, because remember this is volume of HCl added plus whatever your initial volume was, will give you what the pH is in this region. Okay, so those are the features of a weak base titrated with a strong acid like HCl. All right, so it's kind of interesting. I think this is what it is. So now the last thing that I will mention, and that's something we don't always touch on, is just this little hump here, and that's actually just for completeness. That's how a real titration curve of a weak acid and base will look like, and that's something that happens outside of the buffer region. It's before the buffer is the buffer actually sets in. It's before your base or before your conjugate acid actually starts to form. You will see this little kind of spike to form in the pH curve. You do not have to really draw that in. You can assess it as such, but the data I was plotting to make this curve had that in, so I kept it in because a real pH curve or titration curve would have this little spike in here, which is an interesting, well, not artifact, but an interesting fact about how real titration curves look. They first will have a little spike, and then they go into all these theoretical details that we technically look at. All right, just because the system takes a while before it actually starts buffering itself. So initially the pH will slightly rise, and then it will start going into the buffer region. All right, cool. So our last question then was on indicators. So let's look at what indicators we can use for this titration. So I've got the little graph here that shows some options. And to choose an indicator, we must look at what our endpoint pH was. So our endpoint pH was 5.93 naught. So that's round about here. And so anything really that fits in this region will work. But I think the best option is the one that has or the best indicator would actually be bromocresol purple, because you notice that it changes color exactly in the middle, or meaning that it has a range that works exactly in the middle of our endpoint. So meaning that it would work perfectly for our pH or for our endpoint, right? So meaning it has a active range within our endpoint range. So meaning it would be able to change color all the way from 6.5 to about, no, that's 5.2. So meaning if we were to have our endpoint is at 5.9, so meaning it would be able to indicate our endpoint at 5.9. One that also could work, alizarin, could also work. It still cuts in here. I mean, you could in principle use Aerochrome black tea. I mean, it's also there. I wouldn't say methyl red would work because it's just like at the it's at the start of it. So anything, I think the best option is bromocresol purple. All right, because it lies nicely in between there. So if it's slightly higher or slightly lower, it would still cover us quite nicely. So our endpoint dictates what we must choose. All right, and then hence we would see the color change because it's in that area where this pH indicator is active and would be able to indicate to us where the color change is. All right, so that is it. That is the end of this. Well, that's the end of this. Or this. Of this question. A very long question, very long titration question. And I hope you enjoyed constructing your own pH curve for a weak base and a strong acid. So another long video, and I'll see you in the next one, as always. All right, goodbye. Thank you for watching.